In this video, we'll be graphing a quadratic relation from vertex form. We're actually going to do three different ways, but one of the ways is related to what you're going to learn in grade 11. So that would argue that is the preferred method. On top of learning the three different ways, we really want to have a strong understanding of transformations before we move on to this lesson, because when you graph a quadratic relation from vertex form, you should really understand the transformation you're applying in order to obtain this new parabola. So we're going to review those ideas that we learned in the previous lessons very quickly. Okay, so based on your understanding of transformations and the parameters AH and K, vertical stretches or compressions affect the y-coordinate of our original points. Remember, it's that vertical distance from the point to the x-axis. So that point can increase, or that distance can increase, or that distance can decrease. If the parabola is reflected along the x-axis, the original y-coordinate will switch signs, right? Because instead of going up, for example, to reach the point, you have to go down from the x-axis. So yes, the original y-coordinate will switch signs. If the parabola is translated horizontally, the original x-coordinate will be changed, because think about the Cartesian plane. If you're going left and right, the y-coordinates are not changing, it's the x-coordinates that are changing. And if the parabola is translated vertically, then the original y-coordinates will be changing, because you're going up and down now. Just think of your Cartesian plane. On top of that, we also quickly mentioned about the order in which you apply your transformations. So we said you have to save your translations for the very end. Okay. Now, whether you want to apply the reflections first or the stretches and compressions first, it doesn't really matter. So I'm going to say stretches and compressions, or stretch and compression, and then reflection. But really, you could have said reflections first. I don't want to spoil too much, but in grade 11, you really learn everything you learned in this, learn about transformations in this course with a few little added details. Because in grade 11, you learn about reflections or with respect to the y-axis, and you learn about horizontal stretch and horizontal compression. But that's really it. So if you remember everything from this course, it will be very helpful when you learn about transformations in grade 11. So one thing I didn't go into detail is why we want to save translations for the very end. So I'm going to give you an equation to help you understand why you want to save translations as the last one to apply. Okay, so here A is 2, H is 0, and K is 2. So you would hopefully say vertical stretch by a factor of 2, vertical translation 2 units up. Now hopefully you won't say vertical translation 2 units up, then followed by vertical stretch by a factor of 2. Because if that is what you said, your equation should look like this. Okay? This is a vertical translation 2 units up, followed by a vertical stretch by a factor of 2. You're basically following bed mass, right? This one you're multiplying by 2 first, and then you're adding by 2. You're taking x squared multiplied by 2, and then add by 2. So here, you have to take x squared, add by 2, and then multiply by 2. So that basically explains why we save translations at the very end, because think about vertex form, right? Think about vertex form. What do you do at the very end? You add by k, right? You take x as h, all squared, multiply by a, and then you add by k to solve for y. So based on what vertex form says, that is why we should save translations for the very end. Okay, so if this paragraph makes sense, and if the order in which you state or apply transformations makes sense, then we can put it all together and come up with this. This is called our mapping rule, okay? And this is the method in which you're going to apply or graph transformed relations in grade 11, okay? X becomes x plus h because you applied a horizontal translation. H affects the x-coordinate, like we said earlier. What about the y coordinate? Y becomes ay plus k because your vertical stretch or compression affects the y. And then you followed up with a vertical translation. If you apply translations first, you would y plus k and then all multiplied by a. But that's not the case. It makes sense to say ay plus k because it stretches and compressions with a reflection and then translation. So that is beautiful. That's our mapping rule. Okay, so that's what I'm going to use, that method of mapping rule to graph this, this parabola here. So I'm going to first start off by writing out or stating the values of the parameter. A is -2, h is -1, k is 3. Okay, be careful. H is -1. And that makes perfect sense to me because when I see x plus 1, I want to undo the addition of 1, which means I'm shifting 1 to the left. Anyways, let's write down the mapping rule. Your original xy values become x minus 1, -2y plus 3. And when I see this, I speak to myself. Oh, sorry, when I write this, I speak to myself. I go x minus 1, 1 to the left. -2y plus 3, vertical stretch by a factor of 2, reflection with respect to the x-axis, vertical translation 3 units up. Okay, every time you write a mapping rule, you should state the transformations to your brain. So everything is really, there's a connection here between what you see visually and what you write down in terms of the algebra. All right. Now, so this is the rule I'm going to use to find the new coordinates. But what are the old coordinates? What am I transforming? Of course, our old friend, y equals x squared, the original parabola. Okay? And if you're talking about the original parabola, you want to work with the original vertex, right? And the points around the vertex, so you can get a beautiful transformed parabola. And you should really memorize these points because you're going to use this over and over and over again. For example, you wouldn't, like, I'm going to graph the original parabola. I don't need to, but I will. Something looks a little weird. It's okay, we'll follow along. Okay, y equals x squared. You don't want to just grab these 3 points, because if you grab these 3 points and transform them, you're going to end up with something like this. That's your transformed parabola. You want to grab these 5 points. So when you transform these 5 points, you get a beautiful parabola, or the key, like the nice points that will allow you to sketch a very nice parabola. Okay, so that's why whenever we grab or transform the original y equals x squared parabola, these are the 5 points we use. The center of the parabola and 2 points left of it and 2 points to the right of it. It makes sense. Okay, so now the next table will be the points of my transformed quadratic. So take all my x values, subtract by 1. So it's -3, -2, -1, 0, 1. I'm going to take all my y values and multiply by -2 and add by 3. -8 plus 3, -5. -2 plus 3 is 1, 3, 1, -5. Beautiful. I see symmetry here. The y coordinates have symmetry. Of course they should. I'm graphing a parabola still, right? So, let's see. Let's plot these points. 0, 1. -1, 3. -3, -5. Okay, oops. Let me erase down a second. Okay, let's label that. There we go. So that's how you really graph transformed quadratic relations in grade 11 as well. You state the parameters, develop the mapping rule, grab the original points, use the mapping rule to find the location of the new points, and then plot, 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 connect the dots. Okay? So there are actually 2 more ways to graph a transformed quadratic, graph from vertex form. So I'm going to do the mapping rule way and the additional other methods. I would argue the other methods are much more quicker, but at the same time, in grade 11, those methods don't really work. Okay, they only really work for quadratics based on the special properties like the symmetry and the second differences being constant. Because not every relation has second differences which are constant. Not every relation will have a graph which is symmetrical. So these little tricks, they only work for quadratics. So that's why I'm not very keen on using them, but I'll show them to you anyways. Okay, so a is 2, h is -3, k is -4. You know, right when I write those down, I immediately tell myself what the transformations are. So it's a good habit to do that for yourself. So I wrote down the mapping rule. I write down the original points, 4, 1, 0, 1, 4. Okay, and now subtract by 3, so it's -5, -4, -3, -2, -1. Bam. Okay, then here, 2 times 2 minus 4. Beautiful. So that was one way of doing it, which we already talked about. So the second way to graph y + 2 times x + 3 all squared minus 4 is really, if you think about it, you can come about to this table without doing all this work, right? Because HK, the vertex, this is vertex form, right? You already know the vertex, right? HK, the vertex is -3, -4, right? So you can just plot the vertex, -3, -4, and then you just use this equation and find 2 points to the left of it and 2 points to the right of it. So I'll ask myself, what is y when x is -2? What is y when x is -1? Well, if you plug it into the equation, when x is -2, you can evaluate, you will get a y value of -2. When x is -2, y is -2. So x is -2, y is, bam. What about -1? Punch it into the formula, or the equation, and you get y is 4. So find 2 points to the right, 2 points to the left. And then I know the symmetry. So really, you can just jump straight to this table. Okay? Right there. You can label if you want. You know what? Let's label it. Why not? Okay. So, you know what? Let's talk about this one. So, from here, for example, I don't need to do the mapping rule, okay? Let's just write down the key points that I will get from this table. I need 5 points, okay? Why not? 5 points would be beautiful. So, -4, 9. That is the vertex. I find 2 points to the left, 2 points to the right. So, -5. -6, -3, -2. Bam, bam, bam. Now I solve for the y values. Okay, so that's another way of graphing without using the mapping rule. And this only works because what you're graphing is symmetrical, and you can obtain a vertex here. Not everything you graph will have a vertex. So it's like I said, it's because the quadratic relation is the numbers work out so nicely. That's why there are these alternative methods that also work when it comes to graphing a transformed quadratic relation or transform relation period. Since I already have the table, I really want to give you these numbers, but at the same time I don't, because I'm going to show you the third way of graphing. Okay, so the first way is mapping rule. The second way is just grab the vertex and then find 2 points to the left of it, 2 points to the right of it. The third way is called the step pattern. Okay, whenever I say step pattern, I think of a song. But anyways, the step pattern, you want to think of the original step pattern. Okay, the original step pattern comes from your original parabola. Okay, I'm going to graph the original parabola. So 0, 1, 4. Okay, you can do 9 as well if you want. You know, let's do it. Why not? So this is y equals x squared. Okay, this is your original step pattern. The original step pattern, think about it. If you're at the vertex, to reach the first point to the right, okay, you go 1 unit over, and how high up do you have to go? The first step is 1, okay? You have to go 1 up from that point. And then the second step is to go 1 over, and then you have to go 3. And then the second step is really 5. You can keep going on and on and on if you want. But this makes sense because the first differences are grown by a constant amount. And when it's y equals x squared, the first differences will be 1, 3, 5, and then so forth and so on. Okay, so now you want to ask yourself, what is the new step pattern? Okay, what is a new step pattern? The new step pattern is determined by what your a value is, because this is now going to change the size of the step because you're vertically stretching or vertically compressing. Well, in this case, I'm vertically compressing by a factor of 2. So these steps are half the size. And in fact, we're also adding a reflection across the x-axis. So we're actually, quite a few things are changing. Now it's no longer 1, it'll be -1/2. -3/2, -5/2. To obtain the new step pattern, you just take the original step pattern and multiply it by a. Okay, so this is how you graph a transform parabola using the step pattern technique. So you plot the vertex, which is very easy. Okay, and you ask yourself, what's the first step? -1/2. So you go 1 to the left or the right. I'm going to go to the left because it's blocked off over here, so it's nice and clear. 1/2 down. Beautiful. What's my next step? 3.5 down. Or yeah, 3/2. So 1 to the right, 3/2. Boom. And then symmetry. Beautiful. Usually when we graph a quadratic, we just need 5 points. Okay? We don't need 7. Can you give 7? Sure. Go 2.5 down. Okay, from here, 2.5 right there. Okay, if that's what you want, that makes you happy. But yeah, that's a step. So that's why I didn't want to film this this table, because I want to show you it actually works out beautifully. I promise you they will give you the same answer. So this would be -8.5. You can check using the formula or the equation, sorry, of the quadratic, and then 7. Oh my gosh, it's +8.5. I'm crazy. +8.5. +8.5. And this is 7. Okay, so let's summarize this. You can use the mapping rule technique. This is the preferred technique because this is what you're going to do in grade 11. Okay, there's no step pattern for all the other things you're going to transform later on. So there's a mapping rule, and that's really nice because it really ties together everything you learned in terms of transformation. There's this where you just use a table where the middle of the 5 points is your vertex, and grab 2 to the left and 2 to the right. And then you have this third method of graphing from vertex form, which is using the step pattern. So the original step pattern is because you're always transforming y equals x squared, so that's where that original step pattern comes from. And your new step pattern is dictated by what your vertical stretch or compression factor is, and if there's a reflection across the x-axis. So just for good measure, I'm going to write the step pattern here. The new step pattern, if the original step pattern is 1, 3, 5, then the new step pattern will be 2, 6, 10. Right? The steps are twice as large because we vertically stretch by a factor of 2. Okay, so that's really it when it comes to graphing from vertex form. Oh, by the way, you might be wondering, what if I want to graph from standard form? We kind of brought this up on another worksheet, but if you want to graph from standard form, you have to learn how to change it from standard to vertex, which you will learn later on, but that's quite a bit of far away. Anyways, I gave you 3 different ways. You choose which one you prefer. But on the test, if we specify which method, then you have to go with that technique.